All right, folks, today we're going to talk about electromagnetic waves, and how different types of waves can interact. So we've talked about mechanical waves already, and I know I've mentioned electromagnetic waves, but I told you we'd talk about it later. Well, now's the time. If you remember, mechanical waves have to have some type of particles or a medium to travel through. Mechanical waves like sound, they don't travel through space because there's no air in space. There's no particles for them to travel through. But electromagnetic waves can travel through both mediums and non-mediums, or what you might call a vacuum, where there's no particles, like out in space. Some examples of electromagnetic waves would be like light or radio waves or gamma radiation. Obviously, light travels through space because we can see the light of the sun from where we're at, and there's space in between us, so there's that vacuum, and those light waves travel through there. And you might be wondering, well, where'd they get this name electromagnetic? And that's a great question. You might remember from our magnets and electricity unit that anytime you have an electric charge or a charged particle, it always, no matter what, gives off an electric field. If that particle happens to also be moving, it also gives off a magnetic field. So we get this electromagnetic wave that involves an electric field and a magnetic field put together. So electromagnetic waves are very peculiar because they all have this constant speed in a vacuum. No matter what type of wave it is, they always travel at 300 million meters per second. Sometimes when we use that in equations, we just put c in place of that number, and that's what we call it is c, or if you feel like you could call it the speed of light in a vacuum. You might see this animation down here. There's an important difference about the speed of light in a vacuum and the speed of light through a medium, though. If that light or whatever electromagnetic wave has to travel through different particles, you can see through this that it goes into the particle and has to be absorbed and then gets sent back out of the particle. And that takes a little bit of time. It's this whole process. And then it's got to go to the next particle, get absorbed and re-emitted. And so anytime we have any electromagnetic wave traveling through some type of medium, it's going to go a little bit slower than the speed of light in a vacuum. As you can see down here, through a vacuum, it just goes straight through and there's no problem. If it's going through a medium, the speed of whatever electromagnetic wave it is totally dependent on what that medium is, what its density is, what it's made out of, what kind of particles does it have, how good is it at absorbing energy, and things like that. So the speed is completely dependent on whatever medium it's through, unless, of course, it's through a vacuum and there's no medium, then it's always 300 million meters per second. If you remember our equation, the speed equals the wavelength times the frequency. If we look at this whole electromagnetic spectrum, we could deduce if all of these waves are going the same speed, or the speed of light, they're out there in space going through this vacuum, then the wavelength is inversely proportional to the frequency. And what that means is that when we have a longer wavelength, we have less waves per second. Or if we have a shorter wavelength, we've got more waves smushed in the same amount of time. And that should be a very simple concept. The electromagnetic spectrum includes things like radio waves, which have the wavelength the size of buildings, all the way down to gamma rays, which are very high energy and have very, very large frequencies, very small wavelengths, the size of about an atomic nucleus, the nucleus of an atom. And then right in the middle of that is this very small portion of the electromagnetic spectrum called the visible light portion. And that's the light that we can see with our own eyes. I like to talk about those because we can see them with our eyes. So the three different types of interactions that light waves can have, the visible light that we can see, and depending on what it's hitting, when a light wave hits an object, it can either be absorbed or reflected or transmitted. If it's absorbed, then that light wave has the same frequency or the same energy as the electrons in the particles of that object. So those electrons just take that energy from the light and absorb it, and then that object has more energy. But that light just goes into the object and it gets absorbed, and that's it. However, if the light wave doesn't match the same frequency or energy, the natural frequency of that object, then it can either be reflected or transmitted. If the object is a solid object that you can't see through, like a mirror, perhaps, then the light wave will get reflected. We might call that an opaque object. It's not transparent. If we have a transparent object like your eyeglasses, then the light goes through it. And we call that transmitted light. And if we have mechanical waves interfering with each other, you learned about this last year in earth science, but they can either, when two mechanical waves hit each other, they can either have constructive, partial destructive, or completely destructive interference. And what that means is if the two waves line up to where their peaks line up at the same spot and their troughs line up at the same spot, then those amplitudes of the waves are going to add up together and give you a resultant wave that has a much higher amplitude. So that amplitude will increase. If the peaks and the troughs of each of the two different waves line up together, so they're the opposite, they cancel, the whole wave cancels out and it becomes zero. And then you can have two different waves that maybe don't have the same magnitude of the amplitude or the same size, and then when they have destructive interference, it's not completely destructive. The amplitude still decrease, but they don't completely cancel out to zero. I like to talk about this in terms of music. So if you've ever been in band or choir and you've ever tried to tune an instrument, or you had two people singing at the same time and they're supposed to be on the same note, but they're a little bit off pitch, they're a little out of tune, then you might hear what musicians call beats, and that's at different intervals. You hear like this wow 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 sound, and it gets louder and softer, and it's really kind of cool. So if you look at this red wave and this blue wave here, they pretty much look the same, right? But if you add them up together on this line down here, you put them next to each other, you'll notice that the red and the blue line up in certain spots, and they're completely out of line in other spots. So when they're in phase or they're lined up, we have constructive interference, and that sound would be louder. And when they're out of phase or they're completely misaligned, then we have destructive interference, and it would be much quieter. And that's what that wow, wow, wow sound is. You hear the louder, softer, louder, softer. And it's really pretty cool. Or if you think about, like, if you, over the summer, if you're in a pool and you splash water in two different spots, or you punch the water surface in two different spots, you have this little ripple, and eventually the ripple will come together. And at certain points, you'll have constructive interference where the waves of that ripple get really high and then really low. And that's another type of interference. I think that's all I have for you today. I hope it wasn't too excruciating for you. Good luck with the rest of class.